morning, sir. I'm John Albert Asuncion, BSME 2A, and this is my video presentation about the reheat cycle. So, first, the problem is a reheat cycle with the two stages of reheating is executed with steam expanding initially from 90 bar and 530 degrees. The two reheater pressure are 10 bar and 0.6 bar, and the steam leaves each reheater at 480 degrees Celsius. Condensation occurs at 0.03 bar. For an ideal cycle, find Q sub A and N. B for the engine, ignore the pressure drop through the sum states and compute with W and N. See what's the steam flow rate from an engine output at 20,000 kilowatt. So first step is to draw the TS diagram for a reheat cycle. Since the two stages reheating cycle is undergoes into two reheaters, and that leads us to 7 states in the reheat cycle. From the steam table, state 1, H1 is equals to H plus 90 bar and 530 degrees Celsius is equals to 3,461.4 kilojoules per kilogram, and the entropy of S1 is equals to 6.7532. State 2, H2 is equals to at a pressure of 1 megapascal and an isentropic expansion, meaning it has the same entropy to that as state 1. So S1 is equals to S2. Using the data, we can get the value of H2 by interpolation. H2 is equals to 2856.32. State 3, H3 is equals to H plus 10 bar and 530 degrees Celsius has an enthalpy of 3,435.2 kilojoules per kilogram. State 4, H4 is equals to H at 0.6 bar, isentropic expansion. State 5, H5 is equals to H at 0.6 bar and 460 degrees Celsius has an enthalpy of 3,446.1 kilojoules per kilogram. State 6, H6 equals to H at 0.3 bar, and we get the enthalpy of 2,690 kilojoules per kilogram. State 7, H7 is equals to H is the fluid enthalpy at 25 degrees Celsius equals to 104.88. VF7 is equals to VF at 25 degrees Celsius. We'll get a 0.001029 meter cube per kilogram. HB is equals to 114.14 kilojoules per kilogram. Pump work is equals to BF7 multiplied by pressure at boiler subtracted by pressure at state 7. Pump work is equals to 9.2580 kilojoules per kilogram. Solving for A, added the thermal efficiency formula for heated, added our QA is equals to H1 minus HB plus H3 minus H2 plus H5 minus H4. Using the values obtained, we get the heat added of 4,652.24 kilojoules per kilogram. For thermal efficiency, we have to solve for the work first. So work is equals to H1 minus H2 plus H3 minus H4 plus H5 minus H6. We get a value of 2,076.38. Thermal efficiency is equals to work over heat added. From the values obtained, we get 44.6%. For the engine, we have W net equals to 2,076.38 kilojoules per kilogram. And the thermal efficiency of the engine, we have the formula of W net enthalpy of steam entering the engine minus enthalpy of saturated liquid at conditioning temperature. So EC is equals to H1 minus H2 plus H3 minus H4 plus H5 minus H7 is equal to 4,661.5 kilojoules per kilogram. We get a thermal efficiency of 44.5%. And for the C, for steam flow at 20,000 kilowatts, formula for steam flow is M is equals to 20,000 kilowatts over W net. Using the values we have, get the values of W net is values we have, we get M is equals to 9.63 kilogram per second. And I continue for the number 2. So the problem for number 2 is the reheat cycle. Steam of 15 MPa, 540 degrees Celsius enters the engine and expands to 1.95 MPa. At this point, the steam is withdrawn and passed through a reheater. It re-enters the engine at 540 degrees Celsius. Expansion now occurs to denser pressure of 0.0035 MPa. For for the ideal cycle, find N. B. A 60,000 kilowatts turbine operate between the some state point except that the steam enters the reheater at 1.25 MPa and 260 degrees Celsius. Departs at 1.8 MPa and 540 degrees Celsius. The steam flow is 147,000 kg per A. Generator efficiency is 96% for actual engine. Find NK, 7, NK, and EK. C. Determine the approximate enthalpy of the exhaust steam if that heat loss through the turbine casing 2% of the combined work. Okay, so the number 2, with a given condition, I have drawn the TS diagram for the ideal reheat cycle. From the steam table, state 1, H1 is equals to 3,421.3 kilojoules per kilogram. H2, enthalpy at 1.9 MPa, we get 2,864.56 kilojoules per kilogram. State 3, H3 is equals to enthalpy at 1.95 and 540 degrees Celsius will give us 3,556.6. State 4, H4 is equals to enthalpy at 0.0035 MPa equals to 2,577.98 752 kilojoules per kilogram. State 5, H5 is equals to HF at 0.0035 MPa will give us 305.56. Pump work is equals to BFS of PB minus P5 is equals to 0.001024 multiplied by 1500.35 equals to 153669 kilojoules per kilogram. So to find the N for a thermal efficiency is equals to W net over QA. So the W now is, so multiplied by 100 will give us the N is equals to 46.61%. So for the B, for a 60,000 kilowatts turbine operates between the same state points except for the steam enters the reheater at 1.95 MPa and the 260 degrees Celsius departs at 1.8 MPa and 540 degrees Celsius. The steam flow is 147,000, generator at 96% efficiency. From the actual engine, find combined thermal efficiency, combined mass flow rate, and combine the engine efficiency. So with the given data, we know that it's still the same stage but the pressure have been changed. For this problem, we draw the TS diagram and for the actual engine. From the steam table, state 1, H1 is equals to H at 15 MPa at 540 degrees Celsius will give us 3,421.3. State 2, H2 is equals to H at 1.95 MPa and 260 degrees Celsius will give us 2,929.7. State 3, H3 is equals to H at 1.8 MPa and 540 degrees Celsius will give us 3,558. State 4, H4 is equals to H at 0.0035 MPa will give us 2,591.48 kilojoules per kilogram. And for the state 5, H5 is equals to HF at 0.0035 MPa is equals to 305.56 kilojoules per kilogram. Enthalpy of steam entering the engine minus enthalpy of saturated liquid at condensing. Temperature is equals to EC is equals to H1 minus HF5 plus H3 minus H2 is equals to 3,744.04 kilojoules per kilogram. Work is equals to H1 minus H2 plus H3 minus H4 is equals to 1,458.352 kilojoules per kilogram. And for the E is equals to work over EC is equals to 38.95. 38.95. So the mass flow rate or the MK is equals to 147,000 kgh over 60,000 kilowatts equals to 2.45 kilogram per kilowatt per hour. Combined work is equals to WK is equals to 3,600 divided by 2.45 will give us 1,469.3878. Combined thermal efficiency equals to WK over EC is equals to 39.24%. Combined engine efficiency is equals to EK over EE will give us 100%. So for letter C, the actual work if the 2% of the work heat lost to 29.3878, so the actual work is equals to WB is equals to WK over 0.94 will give us 1,563.1785 kilojoules per kilogram. And the actual enthalpy is equals to H4 is equals to H1 plus H3 minus H2 minus W will give us 2,486.4215 kilojoules per kilogram.